And we're back. Where we left off, we had asked the question, what's sine of b for a triangle like this one here? We know sine is opposite over hypotenuse for a right triangle, and the dimensions we have are given with 3 as the opposite, but an unknown hypotenuse, so you had to solve for the hypotenuse first, and that would come out to be 5. So sine of b would have been 3 over 5. And that might not be an impressive result to all of us here, but I want you to think about this first of all. Just because you have some known angle doesn't necessarily mean you're going to have a 3, 4, 5 right triangle. However, it does mean that maybe not the size is guaranteed, but the size of each side in relation to each other is guaranteed. For any triangle having that angle that we had here, any triangle with that angle, the ratio of side to side is always preserved. Right, so the 3, 4, 5 right triangle, or the 6, 8, 10, the larger yet less popular brother, the ratio of these sides are the same as the ratio of these sides. And so you can do it for a 300, 400, 500 right triangle, and so on and so forth, which might sound rather pretentious, but let me tell you this. Even though it sounds pretentious, doing similar triangles and doing that sort of thing has been astronomically important, and that is not an exaggeration. Folks like Aristarchus and Eratosthenes used trigonometry, used right triangles, used similarities in triangles to estimate things like the radius of the Earth, things like the distance from Earth to the Moon, things like the distance from Earth to the Sun, the size of the Moon, the size of the Sun. All of these astronomical data points were first estimated using right triangles. And more than that, similarity between them. Another more classic example for similarity for triangles would be, I'm standing next to some tall thing, my shadow measures some distance, and the tall thing's shadow measures this distance. I know how tall I am, and so via ratios of the triangles that are resulting, I know how tall the tall thing is. But from there, let's do a more down-to-earth example, and again, being quite literal in my expression there. So suppose I am standing 1,000 feet away from some building looking at the top. How tall is the building if the angle I'm looking up at is 20 degrees? So pictorially, I would represent that using this beautifully, immaculately drawn triangle here, right? So some point is 1,000 feet away from the base of the building, and assuming the building is vertical and not, say, the Leaning Tower of Pisa or other such buildings that makes a perfect right angle with the ground, I need to know this height. So I need to relate, for a right triangle known angle 20 degrees, the side opposite that angle to the side adjacent. And the function to do that for, the ratio to use that for, is, pardon this typo here, is tangent. Right? Tangent relates opposite to adjacent. So opposite then is, after doing a little bit of manipulation, right, multiplying the adjacent over here, I've got tangent of 20 degrees times 1,000, or about 364 feet tall. So that is how you could use trig ratios to find an unknown dimension in a triangle. In fact, if you have a side and an angle, you're able to say everything about the triangle, right? We got one side already. The remaining side we could obtain via the Pythagorean theorem. And the remaining angle we could deduce by way of the fact that all interior angles of a triangle have to add up to be 180 degrees. So this angle here has to measure 70 degrees. Now, 20 degrees is not a nice angle. I'll concede that, right? This was something I had to use a calculator to determine. It was not 30 degrees or 60 degrees or 45 degrees and that sort of thing. But there are triangles having those special angles. So once again, the nice angles that we made such an effort to learn and understand and be able to quickly compute in the previous unit, we still need now. So whereas the focus of last unit was just you being able to compute them, going forward now, it's going to be understood that you can, and more than that, you can reliably and efficiently do it. So now we're going to do that. We're going to use those computations to find still more things. So here's a table of our nice angles for sine, cosine, and tangent. I could do it for secant, cosecant, cotangent, but this is sufficient. And we're going to talk about now triangles having these nice angles in them. Obviously, 0 degrees doesn't really mean much, because if you have a triangle with a 0 degree interior angle, you basically have a line segment. And if you have a right triangle with not one but two right angles, you don't actually have a triangle anymore. So that leaves us with these three special cases to consider in the context of right triangles. Now the first one is the 45-degree angle inside a triangle. If you have 45 degrees being one interior angle, then that's going to guarantee that the other one is also 45 degrees. Because, well, the whole thing has to add up to be 180, so that's what has to happen. But more than that, here's what else you get from it. Right? I have here all of these things that I say. And all of these things are equivalent, which means if you have one, you have them all. Conversely, if one is not true for your triangle, then you do not have them all. But if you have a right triangle, and so much as one interior angle is 45 degrees, that means that the other angle is 45 degrees. It means that sides A and sides B, the two legs, not the hypotenuse, but the other two sides of the triangle, are of equal length. It means that the hypotenuse is the square root of 2 times larger than the remaining side. And that, again, you can obtain by way of the fact that sine of 45 degrees or cosine of 45 degrees, either or, guarantees that the ratio of side to hypotenuse is root 2 over 2, or 1 over the square root of 2. So one side is equal to root 2 times that side for the hypotenuse. Also, by way of the fact that tangent, being opposite to adjacent, is 1, guarantees that the two sides, A and B, are equal. Also, it means that if you were to take the length of your hypotenuse, if that's what you had as your known dimension, and divide that number by root 2, you get the length of the remaining sides. And also, because we have equal angle measures here, that guarantees that triangle ABC is isosceles, but also it's the only isosceles right triangle in existence. There can be no other. So you get all of these things just from that one thing. Or I guess any of the other things for that matter. So 45-45-90s are nice from that perspective. They're nice from a design perspective, because here's a picture of it. Here's the 45-45-90, and it has a lot of nice properties from a design standpoint. You go equally high to the right or the left, you go just as high up or down. So that's kind of nice. And also, even though there's 3 special angles, you only have 2 special triangles to worry about. Because the other, the 30-60-90, right, recognizing that if one of your interior angles is 30 degrees, then that necessitates the other being 60 degrees, or conversely. And so based on that, we can use our trig ratios to deduce and to recognize that, okay, the ratio between adjacent to hypotenuse, the cosine of 60 degrees is a half, which means this length, this adjacent side, has to be half the length of the hypotenuse, or otherwise, the length of the hypotenuse has to be twice the length of the adjacent. Similarly, at a 30 degrees, right, that's a little more complicated, but the tangent of 30 degrees was equal to the square root of 3. No, I'm sorry, 1 over the square root of 3. That's better. 1 over the square root of 3. And so, tangent of 30 degrees equaling the ratio of opposite to adjacent, we recognize that whatever your opposite side is, the adjacent side has to be root 3 times longer. That would give you then the appropriate ratio. So if, say, this side had been, say, 12, for instance, then we know right away that this is of length 24 on the hypotenuse, and the other side is now 12 root 3. And we get all that almost immediately by way of the fact that we're on a special triangle. And so in our next class, we will start to look at special triangles and try and quickly deduce, quickly solve for remaining unknown dimensions of triangles. And then we'll see some applications too as well, I do believe. So that is it for this video. And let me know in your questionnaire coming up what you want to see more of, what you're struggling with the most about this sort of thing. And I will see you in class. Have a good one.